Math 2414, arc length, video 5, the arc length function. The concept that I'm about to introduce to you is going to look almost exactly like what we've just done. The only difference really is the perspective from which you view it. And the arc length function is a critical piece of information or a critical tool that is used in multivariable calculus, also called calculus 3, and is also used in physics and engineering. We start with some function f of x continuous on some closed interval a to b. So here's a graph of that. If we have that, then we can define a new function called s of x, lowercase s for arc length. And that function will give the arc length of the graph from its beginning to some arbitrary point in the middle. So for example, let's say that we have this graph of f of x from a to b, and the initial point would be a comma f of a. The purpose of the arc length function is to answer the question, if I go over to a certain x value and go up to the point on the graph, that would be x comma f of x. How far have we traveled? And the answer to that is s of x. In physics and engineering, usually instead of x, it's t, and the arc length function answers the question. If I'm traveling along a path, after I've traveled a certain amount of time, how far have I traveled? So how do we set this up? Well, it's actually pretty easy, because we have an integral that calculates arc length. It's the integral from a to, oh wait, we're not going all the way to b, we're stopping somewhere in the middle. And it's the square root of 1 plus the square of the derivative. But here's where we have to make a slight altercation. We can't put x and dx here, because when you have a letter representing a limit of integration, it cannot also represent the variable that you're integrating with respect to. In other words, x can't be the integral of the variable of integration and an upper limit simultaneously. So how do we overcome that? Well, we overcome that by remembering that the actual variable that we're integrating with respect to is completely irrelevant. So we can change these x's here to whatever we want. Let's use t.
Hi. I was going to talk to you about the hand badger.
Okay, well, I'm in the middle of the video right now.
Oh, but I want back.
Get it. All right. So yeah, just don't ever have the variable and the limit of integration match the variable that you're integrating with respect to. The whole world will come to an end, metaphorically. All right, so given any function, we can create a new function that answers the question, how far have I traveled once I've reached a certain point on the graph? So why don't we just do one example and make this the last video? Let's do, oh, I don't know. You know what? I think I am going to start a new video because I want to pick a good juicy function that's going to get nice and ugly to let you know that it's not always peaches and cream, and I see the exact one I want to use. This is going to get interesting.